us from Tutor. Today we're going to be looking at dynamics of a particle moving in a straight line, an introduction to it. So, first of all, weight is mass times gravitational field strength. And depending on which exam you're going to take, it's either 9.8 or 9.81. The 2 significant figures or the 3 significant figures, so check with your teacher. Force is mass times acceleration. Now direction is key in mechanics, so if you're taking forces in this direction, you have to take acceleration in this direction. So say if it's decelerating, that means your acceleration is going to be negative. Okay, and we're going to look at 3 basic questions. So the engine of a van of mass 400 kilograms cuts off when it is traveling along a straight horizontal road at speed 60 meters per second. It comes to rest without the brakes being applied, and in the model the assumption is that the van is subject to a constant resistive force of magnitude 200 newtons. How long does it take for the van to stop? So we want to find the time it takes to stop. First of all, let's use force is mass times acceleration. Let's take the forces in this direction. So 200 newtons is a force pushing it in that direction. What about the forces going in this direction? 0, because its engine is cut off, so there is no longer a force pushing it in this direction. Mass 400 kilograms. Acceleration, we're trying to find it. So, you rearrange the formula, you get acceleration is equal to 0.5 meters per second squared in this direction. So it is decelerating. Now we do a simple SUVAT. We have the acceleration, which is negative 0.5 if we're taking it in this direction. And we're trying to find the time. We have the initial velocity, 60 meters per second. The final velocity, when it is at rest, 0 meters per second. I'm going to use V is U plus AT. You substitute in the values, you rearrange for T, you get T is equal to 32 seconds. Now, how far does the van travel before it stops? Again, it's a simple SUVAT. You already have your acceleration, which is negative 0.5. You have your time, which is 32 seconds, initial velocity and final velocity. So you have a wider range of equations to choose from. So you substitute in the values into, well, the equation that I chose is V squared is U squared plus 2AS, but you can choose a different one if you want. And I got S is 256 meters. Now they might ask you to comment on the suitability of a modeling assumption. Here we assumed that the van is subject to a constant resistance force of 200 newtons. And if you're going to comment on the suitability of that assumption, well, air resistance, for example, is unlikely to be constant. Okay? Air resistance unlikely to be constant. That is a comment on the suitability of the modeling assumption. A lift of mass 250 kilograms is moving upwards with constant acceleration. We have Albert and Bella are in the lift, and the floor of the lift exerts a force of 678 newtons and 452 newtons on Albert and Bella respectively. The tension in the cable is 3,955 newtons. What is the acceleration of the lift? Now, we can't do this without knowing the weights of Albert and Bella. And no, it is not 678 and no, it is not 452 because it's not in equilibrium. So, let's take away everything that's not part of the lift. What will be the tension in the cable without Albert and Bella in it? It will be 3,955, take away 678, take away 452, which gives you 2,825 newtons. Now the mass of the lift is 250 kilograms. What is the force going down? It is the weight of the lift, which is 250 G. So 250 multiplied by 9.8 or 9.81, depending on which exam you're taking. I'm going to use 9.8, 2 significant figures. Okay, so 2,825, the tension in the lift, excluding Albert and Bella. Take away the forces going down, because we're going to use now force is mass times acceleration. We're going to take the forces going up. So 2,825 is going up. The weight is going down. So 250 G negative is equal to the mass of the lift, 250, times the acceleration. Rearrange that, simplify it, you get acceleration is 1.5 meters per second squared upwards. Alright, now find the mass of Albert and the mass of Bella. So now we have to look at the reaction forces. Okay. What are the forces going up for Albert? It is the force exerted from the floor of the lift, which is 678 newtons. What are the forces going down? That is his weight. So mg. Mass times 9.8, the two significant figures. So let's just use forces mass times acceleration. And the acceleration of the lift is the same as the acceleration of Albert and Bella because they are part of that moving body. So we'll take the forces going upwards, 678, take away mg is equal to the mass of Albert, we still don't know that, multiplied by the acceleration. So you simplify it, rearrange it. The mass of Albert's mass is 60 kilograms to two significant figures. I didn't tell you for the acceleration as well, it is also to two significant figures. Because we're using 9.8 to two significant figures, all our answers should be in two significant figures. So if you are doing an exam where you have to use 9.81, then put your answers to three significant figures. Okay, let's do Bella now. So the same exact process, you rearrange it, you simplify it, you get m is equal to 40 kg. Next question. Alright, so a small stone of mass 400 grams is projected vertically upwards in a pond full of water from the bottom of the pond with initial speed 10 meters per second, and it experiences a constant resistive force of magnitude 3 newtons. Assuming that the stone does not reach the surface of the pond, what is the greatest height it reaches above the bottom of the pond? So we're going to find that height. Okay, so first let's find the stone's acceleration. Force is mass times acceleration. We're going to take the forces, let's take the forces downward. So, the force is down, it's 3 newtons. Okay, are there any forces pushing it up? No, there may have been a force to initially project it upwards, but there is no longer a constant force pushing it upwards. Just like the example with the van, when the engine cut off, okay, there's no longer a force pushing it in the forward direction. So, we're forgetting the force of its weight. The weight of the stone is a force going down. Okay? The mass is 400 grams, but we want the mass to be 0.4 kilograms. We want it in kilograms, not in grams, otherwise the equation is not going to work. So the force going down is 0.4 G. 0.4 multiplied by 9.8, the two significant figures, is equal to the mass of the stone, which is 0.4 kilograms, multiplied by the acceleration. You rearrange it, you get A is equal to 17.3 meters per second squared in the downward direction. So it is decelerating. Now because we use 9.8 to two significant figures, the answer here has to also be rounded to two significant figures. But because this is not our final answer, do not round it yet. Round it at the end. So we're going to keep 17.3. We need to find the greatest height reached above the bottom of the pond. A simple Suitability equation. So S is what we're trying to find. Initial velocity is 10. If it reaches the greatest height, that means it is no longer moving upwards and is about to start moving down. So that means at that split second, at that instant when it stops moving upward and starts moving downward, its velocity is 0 meters per second. Acceleration, we just found out, negative 17.3. We're taking it upwards. Okay, and time we don't know. We don't need it. So, the Suitability equation I'm going to use is v squared is u squared plus 2as. You substitute in the values, rearrange the equation, you get s is equal to 2.9 meters to 2 significant figures, because that's your final answer. Okay, next part of the question. Find the speed of the stone as it hits the bottom of the pond on its return. Okay, so we're going to need to draw a different diagram for this. Okay, so now the stone is going to start moving downwards. The reason we've drawn a different diagram is because the acceleration is now different. Okay? Because the resistant force has now changed direction. Okay? Whichever direction you move the stone in the water, the resistant force is always going to be in the opposite direction. So the acceleration is different from when it's going up to when it's going down. So force is mass times acceleration. We need to find the new acceleration. Let's take the forces downwards. We have its weight, 0.4 g, negative 3 newtons, is equal to the mass of the stone, which is 0.4 kilograms, multiplied by the new acceleration which we need to find. Rearrange it, you get acceleration is equal to 2.3 meters per second squared in the downward direction. Obviously the two significant figures, because you used g is 9.8, which is the two significant figures. Now it's just a simple SUVAT. Okay, you have your initial velocity, which is 0. It's at its greatest height, remember. The final velocity is what you're trying to find when it reaches the ground. The displacement is 2.9, but that is a rounded figure. Okay, so use either the fraction or the long decimal which was displayed on your calculator for this new calculation. Okay, so 100 divided by 34.6, I'm going to use that. Acceleration, we just found out, 2.3, two significant figures, but that was the only value that showed up on the calculator, so that's the full value. Time, don't need it. Okay, so let's use v squared is u squared plus 2as. Substitute in the values, rearrange the equation, you get v is equal to 3.6 meters per second to 2 significant figures. Now say you did the calculation in the upward direction, you would get the velocity as negative. But it just asks you for the speed, and speed is a scalar quantity, so no direction, just if it's positive or negative, just give it as a positive value for speed. Alright, for the next part of the question, we have to find out the total time taken for the stone from when it's projected to return to its initial position at the bottom of the pond. So because the accelerations and the velocities are different when the stone is going up and when it's going down, we have to find the time for when it's going up and the time when it's going down and add those two together. So for the first one, we have all our SUVAT thingies. I'm going to use v as u plus at. And for this, I'm going to use s is ut plus a half at squared. I'm just going to race through this because this is not to do with force is equal to mass times acceleration. So the answer is 2.2 seconds to 2 significant figures. This has been the Awesome Tutor. Bye.